Welcome to the final module. Here we move beyond simply presenting credentials and focus on proving only what matters. Selective disclosure and zero-knowledge proofs help verifiers make trusted decisions while users keep unnecessary personal details private. So far, you've built a foundation in identity models, credentials, DIDs, cryptographic proofs, and issuer-holder verifier decisions. Now we'll use that foundation to minimize disclosure, proving the right facts without exposing everything behind them. Selective disclosure matters because most verification questions are narrower than the documents people usually share. A bar does not need your birth date, address, or ID number. It only needs to know you are over the required age. When the proof matches that purpose, the holder reduces exposure, the verifier avoids collecting unnecessary data, and the exchange becomes more trustworthy. Privacy sits on a spectrum. At one end, a raw attribute exposes the actual value, like a full date of birth. A disclosed claim narrows the exposure to one chosen fact, such as country. A predicate proof goes further by proving a condition, like being at least 18, without revealing the birth date. A zero-knowledge proof is the cryptographic mechanism that lets the verifier trust that statement while the hidden values stay hidden. Minimal disclosure starts before any request is made. First ask what decision needs support: access, eligibility, compliance, a discount, or authorization. Then translate that decision into facts, not documents. You may need to know someone is over 18, not their full birth date. Prefer yes or no predicates wherever possible, and reject fields collected just in case. The goal is enough evidence to decide, with nothing extra to retain or expose. From the verifier's side, begin with the actual decision, not the data that might be convenient to collect. If the decision is to allow a purchase, ask what evidence is truly required. Often, that is a predicate, like age is at least 21, rather than a birth date or full ID. Choose the weakest proof type that still supports the decision: disclosure, predicate, or credential possession. Then document the necessity, so every proof request has a clear privacy justification. Consider a student discount flow. The application requirement is simple: prove this user qualifies. A privacy-preserving proof turns that into narrower checks. The credential was issued by a trusted university, the enrollment status is active, and, if needed, the institution is in an approved partner set. Everything else is out of scope. The verifier does not learn a student number, GPA, address, birth date, or transcript details, because those fields are not necessary to decide eligibility. In a typical flow, the verifier asks for specific claims, such as age over 18, and includes a fresh challenge or nonce. The holder's wallet finds credentials that can satisfy the request, then asks the user to approve what will be revealed. Using the credential, holder secrets, and nonce, the wallet creates a proof instead of sending the full credential. The verifier checks the proof, issuer trust, revocation status, and whether the policy is satisfied. A privacy-preserving presentation is not a copy of the credential. It is a tailored proof package. Some claims may be disclosed because the verifier genuinely needs them. Other claims remain hidden, while still being cryptographically tied to the issuer's signature. Predicate proofs answer questions like, is this person over 18? Without exposing the birth date. Challenge and domain binding make the proof specific to this session and verifier, so it cannot be replayed somewhere else. For developers, selective disclosure may look like a single SDK call, but the surrounding checks are essential. You pass the signed credential, the fields to reveal, any predicates, the verifier's challenge, and the holder's key material. The SDK derives a proof without changing the credential. The result is a verifiable presentation containing only the approved claims plus proof artifacts. Always bind the proof to the verifier's request and require holder consent before generation. Age verification is a clear example of a predicate proof. The credential may contain a signed birth date, but the wallet does not disclose it. Instead, it evaluates the verifier's rule, such as over 18, over 21, or within a teen range, and generates a cryptographic proof. The verifier learns only the result. Because age changes over time, the proof also needs a trusted current date and a freshness check. Membership predicates answer one question: Is this holder inside an approved set? The proof might show they belong to an approved employer, qualify for student benefits, or come from an allowed region, without exposing an employee ID, student record, or full address. The key policy choice is precision. Does the verifier only need eligible, or must it know which group qualified them? That choice determines how much remains hidden and what evidence the proof must bind to. Threshold predicates apply when eligibility depends on meeting a minimum, not revealing the exact number. A certifier can prove someone completed at least 40 training hours. A lender can verify a credit score clears 700. A bank can confirm a required deposit is covered. The verifier learns only the pass result, while still checking units, freshness, trusted issuer, and revocation status. With zero-knowledge credentials, verifier policy becomes less about collecting fields and more about accepting the right proof. The verifier should ask, does this proof satisfy the business predicate, such as over 21? Was it issued under a trusted schema by a trusted issuer? Is it unexpired, not revoked, bound to this challenge, and intended for this domain? Finally, log the decision, not the hidden inputs, or the privacy gains disappear. The core pattern is simple. Design the policy around what must be proven. Generate a zero-knowledge presentation that reveals only the needed claims. Then verify the decision. Age, membership, eligibility, and score predicates all follow this model. Next, we'll make it practical with SDKs, threat modeling, and the capstone.